All right, why don't we get started? It is an absolute pleasure to welcome Dr. Kartik Srinivasan today. Kartik has, in my opinion, a very impressive resume. He's published over 100 peer-reviewed papers. Those papers have garnered more than about 12,000 citations. He's a fellow of the Joint Quantum Institute. He's a member of the technical staff at the National Institute of Standards and Technology in Gaithersburg, Maryland. He has a number of awards. Most importantly, though, as a scientist, he's made really important contributions to the fields of nanophotonics, nonlinear optics, photonic crystal cavities, as well as quantum optics. And today he's going to be telling us about chip-integrated nonlinear light sources for deployable quantum technologies. Thank you so much, Kartik. I look forward to your talk.
Hey, great. Can I just confirm you're able to hear me okay?
Yes, we can hear you okay.
All right, great. Yeah, so thanks, Ryan, for the introduction. And yeah, I really appreciate this opportunity to speak to you all remotely. It'd be great to visit in person because Flagstaff is beautiful, but very happy to have this opportunity to talk to you about the work we've been doing at NIST and the University of Maryland. Like Ryan said, we're basically trying to develop chip-integrated kind of nonlinear optical devices to try and help support sort of deployable quantum technologies. So, one thing I wanted to mention is I can't really tell if there's questions or anything, but please feel free to interrupt, just speak up, or Ryan, maybe if there's a chat question or something, you can let me know. So, in terms of the reason why we're kind of doing this work is, it's really motivated by the fact that photonic quantum technologies, they really operate at a wide range of wavelengths due to the, very different physical systems that are being studied. So you have systems like trapped ions and trapped atoms that have their transitions sometimes in the UV or the visible, and they're useful for things like clocks and magnetometers and atom interferometers. And then we have solid state quantum emitters, things like color centers in diamond or indium arsenide quantum dots, being used for applications like magnetometry and the generation of quantum states of light. And they have their transitions sometimes on the redder side of the visible, also in the near infrared. And then, of course, we have the telecommunications bands around 1550 nanometers, which is really distinguished because of the very low propagation losses in optical fibers at those wavelengths. And so nonlinear optics really provides a very kind of natural way that we can think about being able to connect these different wavelength bands together. And we think about this in a few different contexts. So on the one hand, we're really interested in coherent control. So being able to generate the coherent states of light that we need to drive some of these different quantum systems and interrogate these different quantum systems. We're also interested in being able to create sort of precision metrological tools like frequency combs that we can use to perform measurements on the quantum systems. And then, maybe in kind of more futuristic sort of applications, we would like to be able to really network these quantum systems together through techniques like quantum frequency conversion, where you can directly interface, the quantum states of light between the individual nodes in a network. Ideally, what we want to be able to do is realize all these different nonlinear optical functionalities in integrated photonic circuits. So these are circuits that are really based upon this kind of fundamental unit of an optical waveguide that's then integrated into various types of geometries, all within, kind of a single platform. So what I want to do is spend a few more minutes talking about some of the, kind of specific applications of nonlinear optics that people have historically, studied, and then talk a bit about why nanophotonics in particular is an interesting path forward for trying to realize nonlinear optical functionality. I'll then spend a little bit of time talking about some of the ingredients that are needed to realize efficient nonlinear optical processes in nanophotonic devices, and in particular, nanophotonic resonators. And then I'll spend a bit of time talking about our specific kind of experiments and sorts of applications that we've been looking at. So I was a little bit ambitious in my abstract, and I listed a number of different things, but I'm really going to focus on the ones on the left-hand side here. So work where we're developing on-chip optical parametric oscillators in order to create coherent visible emission at different wavelengths in order to be able to drive different quantum systems eventually, and then work on microresonator frequency combs to try and help support deployable optical clocks. And so the things I have on the right are kind of more explicitly quantum, sort of applications, generation of entangled photon pairs, and the frequency conversion of quantum states of light. And if there's any questions about this type of work, I'd certainly be happy to talk about it. I'll come back to it very briefly towards the end of my talk, but I thought it would be better To limit the number of things I was talking about and hopefully be able to provide a little bit better introduction to what we've been working on. Okay, so just kind of make sure we're all on the same page. When I'm talking about nonlinear optics, I'm basically talking about a medium, an optical medium being described by some electronic polarization that really describes the response of that medium to an applied electromagnetic field. And so that a nonlinear optical medium is one in which this polarization has a significant nonlinear component. And this nonlinear component, of course, scales nonlinearly with the applied electromagnetic field. And from our perspective, for this talk, what this nonlinear optics does, what this nonlinear polarization does, is it really enables the ability to generate output optical frequencies that differ from the input optical frequencies that you send into your system. So this is really well known, obviously, in optics laboratories. It's there all the time in some of the different systems we use. There's processes like second harmonic generation or sum and difference frequency generation. And that really extends the range of wavelengths that we can access from what you can directly generate at the output of kind of direct bandgap semiconductors and crystals. So this is a kind of a nice graph that I pulled from the Optical Photonics website that shows some of their continuous wave laser offerings going from wavelengths of about 200 nanometers all the way out to the mid-infrared at about 4,000 nanometers. And my point here was to just indicate, and their point was to indicate, all the different wavelengths that are being accessed through nonlinear optics, particularly kind of in this mid-infrared side, also on the UV side. But there's also important sort of gaps in visible wavelengths that currently, are really only accessed through nonlinear optics. In terms of metrology, nonlinear optics is also often used. Sort of canonical example is an optical atomic clock. And so the idea with the optical atomic clock is that you take a laser and you stabilize it to some atomic reference. And so this atomic reference is really an environmentally insensitive isolated transition and typically in something like a neutral atom system or a trapped ion. And so in many cases, the transitions of these systems are at maybe the UV or at visible wavelengths. And so you might need some of the nonlinear optics that I referenced on the previous view graph in order to create the color that's resonant with this atomic transition. But once you've stabilized your laser to the atomic transition, you have a good oscillator, but it's oscillating at a very high frequency. It's at several hundred terahertz. And so you can't really directly detect such a high frequency with electronics. And so you use this entity called an optical frequency comb, and the frequency comb basically acts as a divider. So it divides down the stabilized but very, very high frequency at several hundred terahertz range to some countable microwave frequency that's the output of your clock. And these frequency combs are really powered by nonlinear optics, both in order to generate the comb in the first place, but also to be able to really stabilize that comb so it can act as a real precision metrological instrument. So in terms of nanophotonics, one of the reasons why we're interested in, and other groups are interested in using nanophotonics for nonlinear optics is to really be able to build full systems around the nonlinear optical device. And so this is some nice work that's happened in the community recently where nonlinear optical chips, these sort of microresonator chips, are being coupled to very compact laser chips. And then, this is happening in a couple of different incarnations. And on the ones on the left, this coupling is happening by basically bringing the two chips very close to each other. In this incarnation on the right, so-called heterogeneous integration, here the laser gain media is actually being directly integrated on the same substrate as the nonlinear optical media. And so you can think about starting to be able to build systems around the nonlinear optics that are far more compact and hopefully eventually more user-friendly than the kind of tabletop systems that we're used to. The basic idea would be able to take this even further, go from having pump lasers coupled to nonlinear optics to also integrating with many of the other components that we might need for applications like clocks. These are going to be things like photodetectors, filters, couplers, all these sorts of elements that we typically use maybe in a fiber optics laboratory. We would like to ideally be able to integrate all of these things together into one sort of small assembly that would really be something that could be deployed outside of a laboratory. So apart from this kind of scaling and integration that you get with these nanophotonic geometries, there's other good reasons for trying to use nanophotonics for realizing nonlinear optical interactions. And one important point is that when you work with these nanophotonic geometries, you're really confining light at sort of the wavelength scale. And in this regime, you're really able to dictate your nonlinear interactions almost purely through geometry. So this is a little example, and I'm going to come back to this later. But this is a device called an optical parametric oscillator, where we're pumping this ring resonator with a near-infrared pump laser. And by just controlling the specific geometry of the ring, by changing its width or its thickness, we can dramatically impact the output color that we generate from this parametric oscillation device, going from green to yellow to orange. And the reason for this is that it turns out that if you look at light propagating through one of these waveguides, basically the phase velocity of light is going to be a very strong function of frequency or wavelength. And so this means it's a very dispersive structure. But equally important, this dispersion is going to be really sensitively controlled by the specific geometry. So the specifics of the thickness and the width of this waveguide. And so by just changing that geometry by a few tens of nanometers, you can dramatically alter the dispersion. And as I'll get to in a moment, being able to really control this dispersion is a real key to being able to enable nonlinear optical processes. So that's not the only thing. In general, there's several different ingredients that you have to be able to engineer at once in order to get these nonlinear optical processes to work. You want to start with materials that have strong nonlinear optical coefficients, maybe a second order nonlinearity or a large third order nonlinearity. We want these materials to simultaneously have broad optical transparency so that it covers the range of wavelengths that we want to work with. In order to access the nonlinear response of the medium, even if you have large nonlinear optical coefficients, you typically need large optical intensities. And then you need to satisfy a couple of rules that are typically present for parametric nonlinear interactions. So one of these things is energy conservation or frequency matching for the output fields with respect to the input fields. And then when you have interactions that occur over some appreciable length scale, then you need to satisfy momentum conservation or phase matching. And this is basically just a similar relationship as this frequency matching, but now looking at the wave vectors of the optical fields instead of the frequencies of the optical fields. So this first requirement of energy conservation, this is something you often take for granted because if you work with like a bulk crystal or a waveguide, as long as you choose the right frequencies, you can satisfy this frequency matching condition. But the momentum conservation condition is non-trivial, and that's because materials have dispersion. So light is propagating at different speeds as a function of wavelength, and so it's typically not trivial to be able to satisfy this momentum conservation. And in kind of classic nonlinear optics, you use things like the birefringence of a crystal in order to be able to compensate for this dispersion. Now, the types of materials that we work with and the integrated photonics community works with are quite varied nowadays. So this is a completely, this is a very incomplete list of some of the different materials the community has been looking at. Broadband dielectrics like silica and silicon nitride and aluminum nitride, electro-optic media like lithium niobate, 3,5 semiconductors like gallium arsenide, aluminum gallium arsenide. There's also quite a bit of work on silicon insulator, diamond, and silicon carbide. The specific material that we're working with is silicon nitride that's grown on top of silicon dioxide on a silicon substrate. And this is a very well-known medium within the integrated photonics community. It has some nice features. It has a pretty broad transparency window going from close to the UV out into the mid-infrared. It has a pretty large nonlinear refractive index. It's about 10 times that of glass. This is a third order nonlinear medium. So I'll be talking about Chi3 processes like four-wave mixing. Other Chi3 processes are things like third harmonic generation. It's a material in which many, many groups have been able to achieve very low losses. So they can create optical cavities that have high quality factors in excess of 1 million. And the 2 points that I've bolded here in red are that from our perspective, one of the great things about this platform is that it's widely available in a number of different research fabrication facilities like the one at NIST, but also at commercial foundries. And the fabrication processes are relatively well understood. And so hopefully what this means is that things that we discover, we can communicate to the overall community and vice versa. So I want to get back to this point about phase matching, which I mentioned is something that can generally be challenging in nonlinear optics due to dispersion. And this connects back to the idea that geometric confinement can be a really powerful control knob in nanophotonics. The basic idea, again, was that the speed with which light propagates through one of these waveguide structures is going to be a strong function not only of frequency or wavelength, but also the specific geometry. Right, and that comes about because the fraction of the field that's residing within the core region relative to the cladding region is both a strong function of frequency as well as a strong function of the specific geometry of the device. And so this ability to be able to control dispersion with the geometry is going to be the knob that we use in order to compensate for the intrinsic dispersion of the materials involved in our nanophotonic devices. So to give a little bit of example of how this all works, I'm going to invoke a specific process called degenerate four-wave mixing. This is a process where we have a centrally located pump at a frequency omega p, and we create a signal that's upshifted in frequency and an idler that's downshifted in frequency according to this energy conservation relationship. Twice omega p is equal to omega of the signal plus omega of the idler. And I have here a representative example where our pump is at 250 terahertz, our signal is at 300 terahertz, and our idler is at 200 terahertz. So in terms of the dispersion engineering, we basically try and choose a waveguide geometry such that this effective index profile, which again, the effective index is related to the propagation constant of light going through the waveguide, we try and choose a specific geometry such that this effective index profile simultaneously satisfies this frequency matching relationship and this phase matching relationship. Now, we typically don't actually work with waveguides on their own. We instead tend to use resonant cavities. And the reason why we use resonant cavities is that we want to be able to achieve high optical intensities. And so if we work with a resonant cavity that has a quality factor on the order of 1 million, that's a relatively small resonator, then we're able to realize very large circulating intensities, something like a gigawatt per square centimeter, even when the input power is on the order of 1 milliwatt or so. And so this makes things very consistent with the types of powers that you can produce with chip integrated lasers, and really thinking about being able to put these things as kind of deployable technologies. We don't require very large pump lasers in order to do the nonlinear optics because we use these resonant cavities. And so within the integrated photonics community, there's a large number of different resonant cavity geometries that one can study. Ryan mentioned some of these sorts of things like photonic crystals, which we've worked on over the years, some of these grating microcavity structures, also so-called whispering gallery geometries where light propagates around the orbit, propagates around the periphery in a kind of circular orbit. And some of the considerations we have, in principle, any one of these cavity geometries can work for our applications, but we have some certain kinds of constraints that we need to consider. And so one is that we're doing this kind of nonlinear optics, and we're trying to do it across widely separated wavelengths. And so we want to be able to realize high cavity quality factors across these widely separated wavelengths. And the second thing is the point I brought up a bit earlier, which is that not only do we want to work in a platform in which we have broad accessibility at NIST and other places, but it needs to be one in which we have in which we're able to exercise a significant amount of fabrication control, because these kind of fundamental requirements of phase and frequency matching are really paramount. So this is the very simple geometry we use for the majority of our nonlinear optics. It's called a micro ring resonator. It's essentially one of those waveguides I've shown that's just wrapped into this circular ring. It's used quite extensively in the integrated photonics field. And the reason why we use it is because it's quite straightforward to realize high cavity quality factors and small mode volumes across a wide range of frequencies. One thing that immediately should become obvious when you use these resonator devices is that you no longer admit a continuous frequency spectrum. Instead, you have these discrete resonant frequencies. And so, this earlier picture I mentioned about, getting energy conservation for free and just worrying about phase matching is not exactly accurate in these resonators. You really have to worry about using a phase match set of resonant modes and then making sure that the relationship between the frequencies of those resonant modes, is precise so that you satisfy the frequency matching condition associated with the nonlinear optical process. One nice thing about these whispering gallery resonators with these circular orbits is that the periodic boundary condition associated with having a circular path basically gives you a very simple mode structure in this azimuthal direction. So if phi is my azimuthal angle, then just by necessitating that the field at phi is equal to the field at phi plus 2 pi, I get this criterion that in the azimuthal direction, my field varies as e to the im phi, where m is some integer mode number. And so when I think about phase matching, the momentum that I'm trying to match is that along the azimuthal direction. And it turns out that this is effectively now quantized by these integer mode numbers. And so instead of having this kind of continuous phase matching relationship that I might have in a waveguide, I have this kind of discrete phase matching requirement that I have in one of these ring resonators that just says that I need to choose my mode numbers precisely so that I satisfy this criterion. In this case, that twice the mode number for the pump minus the sum of the mode numbers for the signal and idler is equal to 0. So if we choose the correct modes in this type of resonator, they're going to be automatically phase matched, but then it's not going to be any old resonator that's going to have those same modes that are frequency matched. what we have to be able to do, just going back to this earlier picture, is that we have to be able to choose a specific resonator cross-section so that the specific discrete modes of this resonator simultaneously satisfy this mode number matching criterion I was mentioning, as well as the frequency matching criterion. Now, one thing that I've kind of swept under the rug is that I've basically intrinsically been talking about where the cavity resonances are without any power inside the cavity. If you actually put optical fields inside the cavity, you can have shifts. Some of these shifts are due to thermal effects because you have some temperature dependence of the refractive index, and because some fraction of the light that you send into the resonator is going to be absorbed and is going to heat up the resonator. And then the other effect is going to be the optical Kerr effect. We're working with a third order nonlinear medium, so there's a Kerr effect, which is just saying that you have an intensity dependent refractive index. So in practice, what we have to be able to do is that we need to be able to consider these nonlinear and thermal frequency shifts when necessary. And for some of the devices we're working with, and indeed eventually becomes necessary to augment, kind of this initial frequency matching relationship that I described with one that takes into account these nonlinear and thermal frequency shifts. Okay, so I hope that's given a little bit of a perspective. I know I went kind of fast, but I hope that's given a little bit of a perspective in terms of how we engineer our devices. We want high cavity quality factors. We would need that to be high across a broad range of wavelengths. We really focus on the geometry of the device in order to get phase and frequency matching to work. And now I'm going to talk about a couple of different application areas that we've been working on. And the first one is with respect to these microresonator optical parametric oscillators. And so the basic idea is shown here on the top. We come in with a single frequency input. We send it into this device and we generate two colors at the output, a signal and an idler. And what we're trying to show is that we have a great amount of control in where these colors are generated so that we might be able to address a wide variety of different physical systems just by adjusting the geometry of the chip that we're working with. And again, the basic idea is this notion that there's this huge range of different physical systems that are of relevance for applications like clocks and magnetometers and different types of sensors. They often have their transitions at visible wavelengths or maybe the short near infrared. And typically in our labs, when we're performing experiments, we're using titanium sapphire oscillators or external cavity diode lasers in order to probe these systems. And, these are wonderful workhorse systems, these lasers that we use in the labs, but they're relatively large and expensive and they weigh a lot. And so they're not necessarily amenable for deployment, in a lot of applications. On the other hand, there's just been really spectacular development in the creation of chip integrated lasers that can be very high performance, particularly in the telecom band. There are groups that can realize sub-kilohertz laser line widths and tens of milliwatts of optical power, using some of this integrated nanophotonics technology. And so the types of things we're interested in are trying to see whether we might be able to create systems that could take advantage of some of these really nice developments in chip integrated laser technology, but now combine it with nonlinear optics so that we can reach some of the important wavelengths for some of these quantum applications for which we might not have good chip integrated lasers at the moment. So the specific process that I'm going to focus in on is the one that I already mentioned, which is this kind of degenerate four-wave mixing process where we have twice the pump frequency is equal to the sum of the signal and idler frequencies. And it's just a little bit of arithmetic, but what you can see is that if I come in with a pump at about 780 nanometers, then in principle, I can generate output colors that on the high frequency side can go all the way up to around 400 nanometers or so. And on the low frequency side, I can go out to wavelengths as long as about 2.5 microns or so. And so, of course, we have to be able to satisfy phase and frequency matching in practice, but just in terms of what's in principle possible, you actually have this ability to cover a very broad range of the optical spectrum using, a single near-infrared laser and very flexible nonlinear nanophotonics. So I already kind of mentioned what some of the ingredients are for these kinds of devices. There's the phase and frequency matching. There's having the high quality factors of the different wavelengths. I should also mention that, of course, it's not enough to just generate the light inside the ring. You really have to be able to extract it well into an access waveguide and then potentially off the chip. And of course, you have to be able to take your input pump light and be able to inject it inside this ring with a high efficiency as well. Again, as we mentioned earlier, we basically engineer our devices in terms of the phase and frequency matching by tuning, the cross section of the waveguide that comprises this ring in terms of its width and its thickness. So this is some work that Dr. Xuan Liu, who's a research scientist in my lab, did a couple of years ago to try and establish that this type of optical parametric oscillation device can be realized in a chip integrated platform. So what I'm showing on the top here, this is an electromagnetic simulation looking at frequency matching in one of these devices. And the zero crossings correspond to the frequencies that are matched, and these should correspond to the places where we generate light. And indeed, this is what Xuan saw in his experiments. When we pumped this device at about 290 terahertz or so, we created an output at about 380 terahertz, so that's about 780 nanometers, and a second output at about 200 terahertz, that's about 1500 nanometers. And it's a relatively low power device. So the threshold for this parametric oscillation device was about a milliwatt or so. The next thing that we looked at is how we would be able to actually tune the output frequencies of the device. And so this is a simulation that's very similar to the simulation I showed on the previous view graph. But what we're showing here is that for the right type of geometry, if we go and we tune our pump frequency very slightly, the zero crossings, which are going to correspond to where we generate our output colors, these zero crossings can quite significantly change. So we can go from a zero crossing that's say at about 420 terahertz to a zero crossing that's all the way at about 520 terahertz or so. So spanning from different, going from the red to the orange to the green. And this is essentially what Xuan was able to demonstrate in experiments. So we took a series of devices and we had this kind of precise geometry, and we did a little bit of tailoring of the geometry as well, a little bit of trimming of the geometry. And then we went and adjusted our pump frequency and went from device to device. And what we found is we look at the aggregate set of wavelengths we were able to cover across this chip, or actually it was a series of 3 chips. What we were able to see is that on the short wavelength side, we could go all the way down to about 560 nanometers. And on the long wavelength side, we went all the way up to about 1200 nanometers. And so this covered wavelengths like in the green, yellow, orange, and red. And so starting to realize some of this potential in terms of wavelength access. And so this is looking at a bunch of spectra from these devices in a little bit more detail. I'm not going to go through every one of these, but the point is that there's just a single pump laser that's a little bit tunable that's being used in this system, and then we're able to access all these different wavelengths that are of relevance for quantum science. So 900 nanometers for indium arsenide quantum dots, in the red for color centers in diamond, including nitrogen vacancy, tin vacancy, some of the rare earth doped crystals that are being used for quantum memories at about 600 nanometers. These are some of getting close to some of the atomic transitions of alkali vapors like cesium and rubidium and so forth. Now, one thing, if you look very closely at the graphs that I showed on the previous, the data that I showed on the previous slides, one thing that you might notice is that typically we don't have a whole lot of power that we're generating into these parametric sidebands. And of course, in a real application, it's going to be important to have appreciable amounts of power. And so what we wanted to be able to study next was, how can we improve the conversion efficiency of these devices? Where we're describing the conversion efficiency is basically a ratio of the flux of photons that we produce into our signal channel divided by the flux of photons that we have in our pump. And so one, very straightforward route to improving the conversion efficiency is something I alluded to earlier, which is really making sure that you have good coupling between this resonator and this waveguide. And I want to mention it's kind of non-trivial when you have these optical parametric oscillation devices because your frequencies are so different. And so it can be difficult to have good coupling at both the pump wavelength and the signal wavelength, for example. But if you are able to indeed realize good coupling of these different wavelengths, then in principle, theoretically, you should be able to achieve conversion efficiencies going from about 25% all the way up to actually 50% if you're strongly overcoupled in a pair of the bands. Now, what my postdoc Jordan Stone started looking at is kind of intrinsically when we've been talking about these optical parametric oscillation devices, we've just been focusing on 3 fields and the 3 cavity resonances that are associated with those fields. But in practice, when we work with these microring resonators, we don't just have 3 modes in this resonator. In fact, these resonators have many, many modes. The free spectral range of the resonator is much, much smaller than the spacing between the signal and the idler that we're generating. And so there's this question, in a realistic device that has many more than 3 modes, are there competing nonlinear pathways that might ultimately degrade the efficiency of the device? And so maybe we can have parametric oscillation, but if we try and push it far above threshold, maybe we're going to see a number of competing processes that really degrade the efficiency of the device. And so what Jordan was able to show through some nice theoretical analysis, which I don't really have time, unfortunately, to get into, is that if you work in the appropriate dispersion regime of the system, a regime in which you have very strong normal dispersion around the pump, you can have a device that acts basically in practice like a 3-mode resonator. And that's sort of what's being shown here in these images. What's being shown here is the region of maximal conversion efficiency as a function of a couple of parameters associated with the device. And what you can see is this region of strong conversion efficiency really gets significantly broadened if we make sure to work with devices that have sufficiently normal dispersion. So we started looking at this in experiments. This is work done by my student, Edgar Perez. This is an optical parametric oscillation device that Edgar has studied. We're pumping the device at about 980 nanometers and generating light at about 780 nanometers and about 1310 nanometers. And this device really puts out an appreciable amount of power. So the efficiency of conversion from the pump to this idler is in excess of about 20%, and we have about 14 milliwatts of power on the chip. And then importantly, what Edgar's looked at is kind of the efficiency of the device as a function. This is shown here of resonator waveguide gap. This is basically a surrogate for the coupling. And so the devices that are very low efficiency, less than 1% efficiency, this is where the coupling is very poor. But if we improve the coupling as we've described, then we can get to efficiencies, approaching 30%, which is what we kind of predicted would be the case based upon the simple theory, provided you're working in this kind of effective 3-mode system. Okay, so I hope that's giving you a little bit of a flavor for what we're trying to do with these microresonator optical parametric oscillator devices. Again, the basic idea is that there's really impressive chip integrated laser technology that's being developed at certain wavelength bands. And of course, we might expect that people will work with new materials and develop those impressive technologies at other wavelength bands. On the other hand, the nonlinear optics can be a really flexible way where you can essentially transform a fixed wavelength laser to one of any number of colors. And the way that we're dictating what colors are generated is primarily through the geometry of the device. So maybe this is a good time. I haven't been paying attention if there's any questions. So maybe this is a time for me to just pause for a moment and see if there might be any questions from the audience.
Any questions? Yeah, got one question.
Should I walk up there?
Yeah, please come up here.
All right, so I was curious on the 22nd slide, what's kind of the limiting factor like for higher dispersion? What's holding you back from making that range larger?
Oh yeah, that's an excellent question. Yeah, so what's holding us back from making this range larger? And the one thing that's quite tricky, one of the things that's quite tricky is that these materials are becoming, very, very dispersive as you go to shorter and shorter wavelengths. It's basically starting to approach, kind of the band gap of silicon nitride is out here maybe at 350 nanometers or so. And so you have some very strong normal dispersion over here in the, say, 400 to 550 nanometer range. It's actually something like an order of magnitude larger than what the material dispersion is, say, in the telecom. So part of what we're fighting against is basically just this strong normal dispersion. And one thing I'll kind of mention, I think I get to it again a little bit later in the talk, is that we're not doing nearly as much with geometry as we can. So these ring resonators are quite convenient. And when they have this rectangular cross section, they're quite convenient to fabricate. But it turns out there's a big variety of different types of structures that you can create. And some of those structures can give you even more compensation for the normal dispersion of the material. And that can be an approach to being able to get to these shorter wavelengths. So at the moment, I don't see necessarily, a fundamental limitation that's going to prevent us from getting down to, say, somewhere in the blue. One thing I'll mention is, if you want to get all the way down to 400 nanometers, that's going to come with an idler that's going to be an exceptionally long wavelength. And so you have to worry about things like absorption losses in the material at very long wavelengths. But to get into kind of the blue at about 480, 470, 460 nanometers, I think it's really technically feasible, but we haven't done so yet. I hope that answered the question.
Yes, it did. Any other questions? I've got a quick question for you, Kartik.
Sure.
Really beautiful work with the OPOs. If you want to use it to address, like an MV center or a narrow transition in an atom, I'm curious about, you must need some tunability aside from what you can do with geometry alone. So I was curious how tunable they are in situ once they've been created.
Yeah, that's an excellent question. Yeah, so like Ryan was sort of saying, I mean, ideally, we want to use this to perform some kind of spectroscopy. And when we think about, a tabletop OPO, the thing is broadly tunable, in many cases continuous. And here we have these discrete resonances. So what we kind of understand at this point is, at least with kind of thermal tuning sort of knobs, we would be able to tune over, maybe a couple gigahertz to kind of a few gigahertz in some cases. And so that might be good enough for doing, some kind of spectroscopy on sort of narrow line width transitions. But being able to go beyond that, really trying to show something that's more continuously tunable is going to be something that I think is going to be a really important thing to try and do, but I don't think it's going to be achieved in these rings on their own. So being able to introduce some kind of in situ tuning knob for the ring would be something that would be very important to be able to do kind of more continuous tuning than what you get from thermal alone. Did that answer the question, Ryan?
Absolutely, thank you. Any other questions? Great, let's continue. Thanks, Kartik.
Sure thing. So let me get back over here. Yeah, so hopefully that gives you a little bit of a sense of what we're trying to do with these optical parametric oscillation devices. I would say there's just a lot of work to be done still to look at the things like what Ryan had just mentioned, to get the devices, once they have enough power to really perform experiments, to really put them through their paces and try them out in experiments and understand some of the strengths and weaknesses of this type of approach. The second topic I had on tap for this talk was to talk about microresonator frequency combs. And so it looks, notionally very similar to what the OPOs look like. It's a type of parametric oscillator, essentially. But here, instead of trying to convert light from a single frequency input to just a pair of outputs, we're basically trying to populate as many modes of the cavity as possible in some sense. And so this is what it looks like in an experiment. I'll get to in a little bit more detail in a moment. And kind of the application space that we're targeting, at least one of them is with respect to optical atomic clocks. So just to take a step back, the optical frequency comb is this, very powerful metrological tool that's essentially a grid of equally spaced output frequencies. And when you have this grid of really precisely spaced output frequencies, you can write the frequency of any one of the teeth of these combs very simply in terms of some overall offset with respect to DC. So that's what I'm calling F0 here. And then some integer index multiplied by the spacing between two adjacent comb teeth that's called the repetition frequency. And so if you can measure and control both the offset frequency and the repetition frequency, then you really have this precision metrological tool that you can use to basically measure any unknown optical frequency and also to synthesize any arbitrary optical frequency. And so one really important thing is that you have to be able to measure and control these two frequencies. And the repetition frequency, you can often just directly photodetect. But the offset frequency can be more challenging to measure. And so what NIST and the Max Planck Institute did in 2000 was basically demonstrate one way to measure this offset frequency. This is the most common approach, which is called self-referencing by the F2F interferometry. And so the essential idea, which can just be captured by a few lines of arithmetic, is that if I take a low frequency comb tooth and a high frequency comb tooth, they should share the same offset frequency. And that means if I double this low frequency comb tooth and then interfere it with a high frequency comb tooth, if I look at this comparison, what I'm going to recover is just that offset frequency. And so this self-referencing is a very, kind of beautiful way to be able to recover this offset frequency, but it puts a really stringent requirement on your comb in terms of needing it to span a full octave in bandwidth. The final thing that I'll mention in terms of this, brief introduction is that one way you can think about these frequency combs is really acting as a kind of gearbox between the microwave and optical domains. And so you really have phase locking between these microwave and optical domains when you use these frequency combs. So about 15 years ago, a group at the time at the Max Planck Institute, Tobias Kippenberg's group, who's now at EPFL, demonstrated that you can actually generate these frequency combs, not using just tabletop mode lock lasers, but actually using these integrated photonic kind of devices, essentially. And the first devices were based upon silica. More recently, there's been a lot of work based upon silicon nitride. And Tobias has written this nice review article that kind of goes through some of the different applications of these microresonator combs. I'm focusing on kind of the metrological sorts of things associated with clocks and synthesizers, but people are using them for LiDAR. They're using them to calibrate spectrometers that are used in exoplanet searches. There's applications in communications and spectroscopy and so on. Again, I'll just mention, I think I already said this a couple of times, that the microcomb functionally is trying to convert a pump into hundreds of modes, whereas before we're trying to convert the pump into just one pair of modes. There's going to be a difference in terms of how we try and engineer devices for these microcombs in comparison to what we do for the optical parametric oscillation devices. But a lot of the ingredients are the same. We're really focusing on tailoring the geometry of the device in order to be able to compensate for the intrinsic dispersion of the material. This is a view graph that just kind of shows that it turns out when you, again, what we're trying to do is convert a single frequency input into this comb of output frequencies. But it turns out that not all states that are supported by the system are really phase coherent, quiet, stable states that are suitable for metrology. It turns out that there's a wide variety of different states that are supported in this damped driven nonlinear system. Some of them are these kind of nice, quiet states that we would like to use for metrology. Other ones are noisy, chaotic, and unstable. But over the years, the community has been able to figure out how to access these phase stable, quiet states. And when you are able to access these phase stable states, it turns out that your experimental data can be pretty well matched by theory. And so the theory of this type of system is basically invokes kind of the nonlinear Schrodinger equation in sort of a mean field limit applied to one of these resonant devices. And I won't go into very much detail. I'll just say that what this equation basically represents is sort of the time evolution of the field inside one of these resonators, and how that time evolution is impacted by some of the basic properties of the device, things like its loss, the detuning between the pump laser and the cavity resonance, the dispersion of the cavity resonances, nonlinearity, and just the driving of the system. And it's through this Lugiato-Lefebvre equation that these types of state space diagrams can be determined. The state space here is looking at the pump power, so kind of the driving field, and then the detuning between the driving field and its nearest resonator mode. So the way that the community often describes the specific soliton states that are supported by these resonators is that they exist, so these are really pulses that are circulating undisturbed as they go around the periphery of this device. And the way that they're able to circulate around undisturbed is due to this kind of double balance between dispersion and nonlinearity, and between parametric gain and loss. And so this is an example of a simulated device. This is the type of thing that we're trying to realize in practice for producing a really useful comb for a clock. This specific comb that we're trying to tailor is going to go down to short enough wavelengths to address strontium optical transitions, and ideally is able to produce reference light for some of the other sorts of things you need to use in operating such a clock. I'll put a little plug here. So many groups have obviously used this Lugiato-Lefebvre equation to simulate their combs. We made kind of a freely available software package on GitHub if anybody would like to have a look at it. So this is our platform for our microresonator frequency combs. It's the same platform as what we use for the optical parametric oscillators. So silicon nitride microring resonators sitting on top of silicon dioxide. You can see here an example of one of our fabricated chips. This is maybe a couple of millimeters across by a few millimeters in the vertical direction. These are some examples of frequency combs that have been generated in the lab, both our lab in Gaithersburg, as well as the lab of my close collaborator, Scott Papp at NIST in Boulder. On the left, these are combs that are pumped in the 1550 nanometer band. You can see that they span a full octave, going from about 1 micron out to an excess of 2.2 microns or so. The ones on the right are combs that are pumped in the 1060 nanometer band. Here we're producing light that's going down to about 780 nanometers and all the way up to an excess of about 1600 nanometers. And so what are some of the ways in which these types of microcombs can be used? Well, one is in an application called optical frequency synthesis. And so the basic idea here, this was a DARPA-sponsored effort, and what they wanted to be able to do was to take a chip-integrated laser and be able to very, very accurately tune its wavelength, have Hertz level accuracy and precision in terms of the output wavelengths that are generated. And so the way that you're going to have such absolute accuracy and precision is to guide the tuning of the laser using stabilized frequency combs, because the frequency comb is your reference ruler. So I can tell my laser, go to this very precise frequency and, take my best shot at getting to that very precise frequency. And then I can actually measure that frequency using the stabilized frequency comb. And if I didn't quite hit the frequency I wanted to hit, then I can feed back on the system until I'm able to do so. So this work was led by John Bauer's group at Santa Barbara. It involved NIST and Caltech and EPFL and the University of Virginia. And the basic result was to take one of these chip integrated tunable lasers and guide its output frequency using these microresonator frequency combs. You can see here on the bottom left, this is the output of one of these lasers, and it's being stepped in increments of just a few hertz. And then here in the center, this is the output frequency generated by one of these stabilized lasers, and comparing what happens when we use microcombs to guide the laser versus when we use a conventional tabletop comb to guide the laser. And you can see that the frequencies are essentially the same. So the microcombs are doing the same job as what the tabletop frequency combs would have been doing previously. This is a second application that we've worked on in collaboration with NIST and Draper and Caltech and Stanford. This is an optical atomic clock. So again, going back to the view graph I showed earlier, the basic idea is that you take a laser and you stabilize it to some environmentally insensitive atomic transition. In this case, this was in a rubidium vapor. This is a small microfabricated vapor cell made at NIST Boulder. And this laser at 778 nanometers is stabilized to a 2-photon transition in this rubidium vapor. So now we have our stabilized laser, but it's oscillating at 380 terahertz. And the frequency combs are basically phase coherently dividing that down to something like a 20 gigahertz output. That's the output of our clock. And what's being shown here on the right, this is the frequency instability of the clock as a function of time. And what we're showing on the bottom, this is for our optical atomic clock. And shown above this is a compact chip scale atomic clock based upon a microwave frequency transition. And so we can realize instabilities that are a couple orders of magnitude better than these compact chip scale atomic clocks based on microwave transitions. But I'll come back to this towards the end. We don't really have a compact system at the moment. So what we have here are basically individual photonic elements that are strung together with optical fibers and lots of BNC cables and lots of commercial electronics and some commercial optics as well in order to get this kind of demo to work. Now, one kind of interesting thing is if you go back and you look at this, part and 10 of the 12 instability of this clock, if you're a real clock aficionado, you might say, well, that's not anywhere near the very best clocks that exist in a lab, at PTB or some other place where you might get a part in 10 to the 17, or at Gilla, where you might get a part in 10 to the 17. And so what Scott's group was able to show was that this is really due to the fact that in this earlier work, we were using these atomic vapors, which of course are very nice in the sense they don't require all the infrastructure of laser cooling and trapping that's required for very high-end clocks. But what Scott was able to show is that if you took a laser that was very, very well stabilized to an ultra-stable reference cavity, and then they divided it down with these Kerr combs, you could realize instabilities at the level of a part in 10 to the 17. So really starting to be able to service, very high-performance metrological systems. And so this is a graph. This is a really nice graph you can find in various review articles looking at how clocks have performed over time. And this kind of inflection point around the year 2000 is when you had the optical frequency comb that was fully self-referenced, and you start to see these optical atomic clocks really start to outperform all these microwave atomic clocks that are in blue. But one thing you might notice if you look at the elements that are involved with these really high performance optical atomic clocks is that their transitions tend to be at visible wavelengths. And all of the combs that I've shown you so far tend to be out in the near infrared. And so we have a couple of different options to try and be able to support these visible wavelength optical clock systems. One is that we can take our frequency combs and try and employ some type of harmonic generation to realize the shorter wavelengths. Or another thing we can try and do is just directly generate the frequency combs in the visible. And so this is what we've been doing. I see that I'm kind of running out of time, so I'm going to maybe gloss through a couple of these slides and just try and hit the highlights. One of the things that we've been trying to do is really compensate for this very strong intrinsic material dispersion we have in devices or in our materials as you go to visible wavelengths. And so this kind of also relates to this question about how can you get the parametric oscillators working at shorter wavelengths. Other things we've been trying to do include trying to make our combs a little bit bigger. I can answer the reasons why if there's any kind of questions. And then trying to address these challenges associated with coupling light between the resonators and the waveguides, especially when you get to these shorter wavelengths. So this is some work. All of our comb work is being led by Greg Moy, who's a research scientist in the lab. A lot of this was originated by Cheng Li, who is a postdoc who's now a faculty at Carnegie Mellon. And what Greg has been able to demonstrate are these octave spanning combs. These are simulations on the right and experiments on the left, where we're starting to generate light in these combs at wavelengths, in the 690 nanometer range. And the 698 is kind of this key wavelength for us because that's the strontium clock transition wavelength. And so we're trying to make these combs, relevant for these types of optical clocks. Another kind of interesting thing that Greg has been looking is, are there different paradigms for the nonlinear optics and the kind of soliton generation that I've described thus far, where there's a single frequency pump that drives everything. And so one thing that we've shown very recently is that if we dual pump our system, so not just use a single frequency at 1060 nanometers, but now a second pump laser at 1550 nanometers, we can harness a broader range of nonlinear interaction in the resonator. So I won't go through this in very much detail, but what basically happens is you take an initial soliton comb that spans over some spectral extent, and by introducing the second laser, you introduce various nonlinear mixing mechanisms, basically the forward mixing analogs of sum and difference frequency generation. And that allows us to extend our spectral extent on both the high frequency side and the low frequency side by a total of something like 60%. So we get a pretty big spectral broadening by using this two pump process. We're still trying to understand the specifics of how these two pump processes can be used in metrology, because of course you have additional complications associated with having an additional pump laser. And this kind of gets to one of the points I made with respect to one of the questions, which is that, you really actually in nanofabrication, you really have the ability to access a very wide range of different structures that that can eventually support very advantageous dispersion profiles. And so this is something that Greg looked at, where instead of having just a rectangular cross section for our ring resonator, we examined what would happen if we etched this small kind of trench. And this was done in a kind of judicious way, because what it allows one to do is to realize coupling between different radial modes of these resonators. And the coupling between these different radial modes of the resonator actually introduces some additional dispersion term in our device. And so we can end up with dispersion profiles that can be quite different than the dispersion profiles we're used to with rectangular cross-section resonators. In this case, the type of state that can be supported, this is all theory, but the type of state that can be supported is what's called a two-color soliton state. So in addition to all the colors we generate around this primary pump around 200 terahertz, we have this second band of spectral colors that we generate. And it's just one pulse that's circulating around the cavity, but now it's distributed into these two spectral bands. And it turns out by engineering the geometry, you can really place the second spectral band at different locations of interest. For example, the one on the top is one that's particularly useful for self-referencing, because one wavelength is centered around 1550 nanometers, and the other wavelength is centered around 775 nanometers, which is the second harmonic of 1550. Okay, other sorts of things we've been looking at as I come to a close, we've been looking at the integration of linear components like various types of spectral filters and so on to process this very large spectral bandwidth with our nonlinear optics like the microcombs. And so this is work that was done by Ashutosh, who's another postdoc in the lab. And then Edgar, the student who I mentioned earlier with respect to parametric oscillation work, he's also been working on using kind of novel lithography techniques, so-called two-photon lithography, in order to create micro optics that might help us be able to put chips together. I'm going to skip this part on other directions. I'll just mention that one can realize these combs in materials like gallium arsenide. I could come back to this if there's any questions, but the real sort of driver behind going to a material system like gallium arsenide, and this was done in collaboration with John Bauer's group at Santa Barbara, is that it is a much higher nonlinearity than silicon nitride. So you can get much lower power devices by switching the material system. This was related to some of the things that we are looking at on the quantum side. I kind of mentioned these two applications, the parametric oscillators and the frequency combs. There's other types of nonlinear wave mixing processes that are useful. There's harmonic generation, which we've looked at in these silicon nitride devices. There's the generation of entangled photon pairs. So it turns out that if you drive these optical parametric oscillation devices, if you keep them working below threshold, you can create pairs of entangled photons. And this is looking at the frequency conversion of single photon states of light. So one thing I do want to do, just in a couple of minutes, if possible, is to just talk a little bit about some of the challenges. And what I would want to say is that, with respect to some of these applications like the frequency synthesis, there's really just a lot of different devices and materials that are needed. So even though maybe, there's only 10 total devices here, so it's not some very complex integrated photonic circuit that has thousands of couplers or something like that. You have 10 pretty highly functional devices that need to be combined together. You need pump lasers to drive frequency combs. You need the frequency combs themselves. You need second harmonic generation. There's the various linear elements for filtering and interference, and there's photo detection. And so this brings about a lot of challenges in terms of figuring out how you put all these things together in a way that makes sense. It's possible in some kind of futuristic scenario to think you could integrate all these materials on one chip, but that's very hard to do. And so people are also exploring kind of hybrid strategies where maybe you take certain pairs of materials and they get integrated together on the same chip, and then you try and make multi-chip assemblies. And so there's a lot of packaging work that has to go into trying to make really kind of deployable technologies here. One other thing I wanted to mention, and this is a little bit of a busy view graph, but maybe we can focus in on the part on the right. This is looking at one of our frequency combs and how this high frequency portion of the comb tunes as a function of the thickness of the device. And the point here is that this high frequency portion is tuning by something like 70 or 80 terahertz, just when we trim the thickness by about 30 nanometers. And so we're looking at something like a 1 or a 2 terahertz shift per nanometer. And so that's something that we've really seen, is that these devices are extraordinarily sensitive to geometry, which I've been plugging as something that's really advantageous, and in some respects it is. But of course, the flip side of having all this sensitivity is how stable can you be? And so it's really requiring a lot of precise fabrication. On the other hand, we've been looking at maybe new designs that can be a little bit less sensitive to geometry. There's new materials one can think about that might also help kind of mitigate the sensitivity. And of course, to speak to Ryan's point, trying to incorporate ways that you can actually do in situ tuning of the devices can be quite important. Okay, so I hope that was understandable, and it's a little bit hard for me to tell without sort of a live audience, but I do really want to make sure that I acknowledge the people in the group that do this work. So a lot of what I spoke to you about today was done by Shiwen Liu and Greg Moy, Jordan Stone, Edgar Perez, Feng Zhu, Ashutosh Rao, Darren Wesley, and Gregory Silogor are process integration engineers at NIST who really help us a lot with our different experiments. We have all these collaborators from NIST Boulder and Santa Barbara. I mentioned some of them. And funding support both from NIST internally to try and kind of promote the development of some of these metrologies and deployable formats, and also from DARPA from these different programs over the years. And so with that, I'm certainly happy to take any questions, and thank you all for your attention.
Thank you so much, Kartik. I'm going to check to see if it looks like John Dallin has a question. So hold on.
Hi, thanks for the talk. It was really interesting. I had a question for your combs that you're modeling in your experiments. So as I understand it, so you want it to span an octave so you can self-reference. But as I understand it, the stability of those teeth kind of degrade as you get farther and farther from the pump or from your central tooth. So on your combs, are those far in, at the end of the octave teeth, are they stable enough to be used as quality optical sources, or are you kind of constrained to kind of the central range of comb teeth?
Sure. Yeah, that's a good question. So I think what you're basically saying is,
Yeah.
okay, maybe we have our pump laser, and then we have our repetition rate, and we have some repetition rate noise, and we're kind of getting this multiplication of that repetition rate noise, kind of all the way to the extremities. And I think it depends a lot on kind of your application, like what type of frequency and stability sort of numbers you need. I mean, certainly to support these kind of clocks operating, I think kind of in this 10 to the minus 12 to 10 to the minus 15 range, I think we're fine. I don't think that we or anybody has done an experiment that has fully characterized how well you can go with these combs. One thing I'll kind of mention, just to give a little bit more context, there are certain noise mechanisms we have in these devices that you wouldn't see in the same way in tabletop devices. And so one of them is thermorefractive noise. So this idea that the refractive index depends upon temperature. And so that's something, for example, my colleagues at Boulder, actually Jordan, who's a postdoc in my lab, did a lot of this work. He characterized the thermorefractive noise as being a limiter on the overall stability of these combs. But then it actually also turns out that you can effectively kind of cool down this thermorefractive noise by using a second laser on the system, basically. Okay. So there's a lot of things to look at. And another thing I could mention is we put these combs in a cryostat before. And if you put the comb in a cryostat, it still functions fine in terms of the nonlinear optics. But the DNDT goes down by a couple orders of magnitude. And so those sorts of things might ultimately help, really push the performance of these kinds of devices.
Okay. Thank you.
Yeah, thank you for the question.
Great. Yeah, Jaime, do you want to come up? I'm going to have the students come up here to ask.
Sure.
Hello.
Hello.
Thank you so much for the talk. So my question was, in your talk, you mentioned that adding a second pump, so you had two pumps, would increase the spectral range. Does that mean adding more pumps, maybe a third and fourth pump would also increase the spectral range, or is that not always the case?
Yeah, I mean, that's a very good question. Honestly, that's something we're looking at in the lab now, basically. But yeah, our understanding basically, so I didn't give a whole lot of detail about the process, but the second sort of nonlinear mixing process that we are referring to is something called Fourier mixing Bragg scattering. And what it basically does is it takes an input signal and it upshifts it and downshifts it by an amount equal to the difference in your two pump frequencies. And this is still going to be subject to these requirements of phase and frequency matching, but it gives you kind of this new pathway through which you can convert light across pretty broad spectral gaps. And so then if you go and you introduce, a third pump and a fourth pump and so on, you'll have all these different possible Bragg scattering pathways, basically, right? Because you'll have all the different possible combinations of these pairwise pumps, for example. And so I think it will certainly, it certainly adds interesting nonlinear physics. Again, one of the things with these combs is, ideally for the application perspective, trying to remain within kind of, this sort of phase stable regime. And so as you add these additional, driving fields, one you're kind of modifying sort of the state space of the system. And so we have to understand better how we, get the benefits of these additional frequency components while still trying to remain within kind of a phase stable operating, kind of window, basically.
Thank you.
Oh, thank you for the question.
Come up, please. Some more students are coming up.
Okay, great.
Hello, thank you for the talk. It's very interesting.
Oh, thank you.
I wanted to ask you a question. When you were talking about, obviously one of the big draws is the tunable wavelength of the chip integrated lasers. And you were saying how you could kind of tune these lasers to get to the exact frequency or the wavelength that you want it to be if it's off. I was just kind of wondering how much error can the initial laser have and it still be tuned to that desired frequency, and how close can you really get to the frequency that you're looking for?
Sure. So let me mention, for these kind of parametric oscillation devices that we've been discussing, and just to recap, so we have a driving laser, and then we have our device that's kind of basically converting the color from, the original driving laser frequency to this output frequency. And so typically, whenever we work with these devices, we need the driving laser to be on resonance with one of our cavity modes. And one way you can do that if it's not naturally on resonance is you can use temperature to bring it onto resonance. And so we can typically do that. And that, I think we don't necessarily need any kind of extraordinary level of accuracy in terms of the nanofabrication. A second thing is that oftentimes, the driving laser itself might be a tunable laser. And so that obviously affords a lot of flexibility because you can tune that laser onto resonance. But maybe the more important question which you were asking is, the output frequency that we create, how precisely can we hit, a very targeted frequency? And what I would sort of say is we don't know, basically. So what we've sort of found is that the nonlinear optics is all very sort of predictable in the sense that if we know our geometry pretty well, then we can very well simulate, the system and realize, the output frequencies, very close to what we actually see in the lab. Very close is obviously like a relative thing, but let's say we can tell to within, 10 gigahertz or something like that. And then I think oftentimes, if we want to get to a more precise frequency, we're going to have these kind of like in situ tuning, like the thermal tuning. The other thing that we've been able to do pretty well is to do some kind of post-fabrication trimming of the device. So we've been able to do things like use very weak chemical etchants that basically remove, sub-nanometer amounts of material, and then they kind of very slightly shift the dispersion and allow you to do a better job of hitting a specific frequency. And so, there are some knobs there. It is very sensitive, and I don't think we have like a full sort of answer in terms of how well we can do. I think we're going to have to pick a very specific sort of application, like perform spectroscopy on some alkali transition, and then, really kind of spend a few months and trying to understand better how well we can do this.
Thank you so much.
Thank you for the question.
Hello. Thank you for your presentation. My
Sure, thank
question,
you.
my question was mainly related on your experimental setup. I
Sure.
saw that you have your micro ring with the waveguide. And have you like taken into consideration like the geometry of your waveguide and how that could affect your coupling regime in terms of like what frequencies you want to see?
Sure, that's a good question. Yeah, so what ends up happening, you're right, like the waveguide itself, is made of the same material and everything like that. And so it should in principle be able to support, nonlinear optical processes as well. But what ends up happening is, our resonator, because of this resonant enhancement effect, because it has this high quality factor in addition to the strong confinement, it basically will see nonlinear optical phenomena at much, much lower powers than our waveguide will. So our waveguide is basically a linear device as far as our experiments are concerned. And the ring resonator is a nonlinear device. But there's actually another class of experiments that people have done with the waveguides alone, where they come in with like a pulse laser source. So they take like a mode lock laser source, and there they have like a high enough power that they can access the nonlinearity of the waveguide itself. And so they do that, for example, to broaden a mode lock laser source and produce like a super continuum or something like that. But for what we've done, we're kind of in this regime where it's only the resonator that kind of matters in terms of the frequencies that we generate, but then the waveguide does matter in terms of being able to get light into and out of the resonator.
I see. Okay. Well, thank you.
All right, thank you for the question.
Looks like we've got a question, another question from the Zoom audience from Madison.
Yeah, hi. I have a little less of an in-depth question, but so the ring resonators geometries, I noticed that they all looked very like nice and like perfect circles. How would their performance change, or would they even work if they're more of like a egg shape or like a racetrack shape?
Yeah, these are good questions still. So I think that what I would say with the racetrack, so definitely, there's a lot of groups that look at these kind of racetrack resonators. And there's good reasons to do so, especially as we try and create larger and larger devices. You kind of waste a lot of space if you stick with the circle. Whereas like with a racetrack, you might be more space efficient, and it doesn't even have to be a racetrack. You can think about other sort of meandering paths. And you basically have to worry sometimes about like transitions between straight sections and curved sections. So you have to kind of engineer those well so that you don't have optical loss, because in a curved section, the optical field is kind of pushed out towards the edge. And in a straight section, the optical field tends to want to be in the center. So, but if you engineer those things correctly, then you can realize low losses in those kinds of geometries. And there are groups that have done so. So we ourselves haven't spent a whole lot of time on that. One thing that we've done, I'll just kind of indulge myself, but we have looked a lot at taking these rings and kind of etching sort of periodic patterning on the kind of the inner profile of the ring, basically. And that kind of periodic patterning can actually be done in such a way that you still retain high quality factors, but it really impacts things like the group velocity of light inside the ring. And so there's actually, quite a bit that one can do with the geometry. And I think, yeah, as a community, we're kind of, only scratching the surface of what's possible. I hope that answered your question. Okay.
Fantastic. Well, let's thank Kartik again. Thank you so much. Thank you so much, Kartik, and you have a great evening. It was really fantastic.
Okay, great. Thanks a lot, and I appreciate all the good questions and the interest, because it's always hard to tell when you give these remote seminars whether you're making sense. So I really do appreciate all the feedback.
Yeah, great. Well, thank you.
All right, take care, everyone.